Hello, my name is José Ramón Martínez. Welcome all to the NATS webinar called Real-Time Simulation with HLA and DDS. In this webinar, we will talk about how the simulation world is evolving and what are the new requirements and the new challenges in simulation. We will talk about HLA and the evolution needed to reach these new requirements. After that, we will present you DDS as a new industrial standard for filling the gaps and achieving these new challenges. We will show you then DDS with some extensions as it's new for some of our audience. Finally, we will talk about how NATS technology can solve and achieve the challenge, joining together HLA and DDS in an established product that is not a promise but a reality. SimWare. The agenda for the webinar will be: first, we will start with a general vision of the world of simulation today. We will talk about the evolution in the standards and the future of them.
You will no longer hear beeps until someone else joins the conference.
Bueno, podemos hablar sin saturación, por favor. My name is José Ramón Martínez. Welcome all to the NATS webinar called Real-Time Simulation with HLA and DDS. In this webinar, we will talk about how the simulation world is evolving and what are the new requirements and new challenges in simulation. We will talk about HLA and Hello, my name is José Ramón Martínez. Welcome all to the NATS webinar called Real-Time Simulation with HLA and DDS. In this webinar, we will talk about how the simulation world is evolving and what are the new requirements and the new challenges in simulation. We will talk about HLA and the evolution needed to reach these new requirements. After that, we will present you DDS as a new industrial standard for filling the gaps and achieving these new challenges. We'll show you the DDS with some extension since it's new for some of our audience. Finally, we'll talk about how that technology can solve and achieve the challenges, joining together HLA and DDS in an established product that is not a promise but a reality, SimWare. The agenda for the webinar will be: first, we will start with a general vision of the world of simulation today. We will talk about the evolution in the standards and the future of them. Second, we will analyze the new trends in simulation. These new trends bring new requirements that current standards cannot reach without evolution. Then, we will propose DDS as a perfect partner for HLA as a well-established way of solving the current problems of the standards and reaching the future. After that, we will show DDS in some depth. We understand that DDS, even though it has almost a decade of history, is new for some of the audience. At that moment, we will reach the point where we will be able to put HLA and DDS in the same picture and show how NATS has done it. No will do it, but done it with his product SimWare. Finally, we will show some success cases of the use of our SimWare technology. Simulation today at a glance. In recent years, there has been a growing demand to use simulation for other purposes than training the individual or team skills as operators of a system. Net-centric operations are requesting the use of simulation systems to train, rehearse, or even analyze and experiment distributed operations. In these operations, different systems interoperate in a network of networks. These requests are one of the main drivers for the quest for interoperable and open architectures in the development of any simulation system, live, virtual, or even constructive. Let me start presenting the actual issues and challenges that we're facing nowadays in the modeling and simulation market with an example. Imagine that you are requested to develop a distributed simulation to train a closed air support operation involving an Apache helicopter, an UAV, a convoy of vehicles, and a C2 system. Apache and vehicle simulations are classical virtual simulators, and the UAV is a live simulator. The C2 system is a real system, interfacing with the virtual environment. The steps you should follow are: select the simulator architecture for the federation. Nowadays, you could have to choose between some HLA, DIS, TINA, or CTIA. Because this is a NATO exercise, you will select HLA because it's the NATO standard and the most used standard worldwide. You will specify the data exchange model and scenarios data models for the federation. Here, you will probably have your first problems because not everything is soundly established in this issue. There are many industry and government groups who are working right now in these issues and how to solve them. For example, NIAG, where NATS is a partner. Third step. You have to federate the simulators. Apache and UAV simulators are HLA compliant simulators. Therefore, it should be very easy to federate them. But what is the meaning of HLA compliance? It doesn't mean that your simulator has an open architecture like defined in HLA, but that it has a specific component in its proprietary architecture that connects the open AP and data model of the HLA federation and its proprietary internals. This is called a gateway, a magic word in simulation that the gateway will use sometimes more. The use of gateways in simulators restrict interoperability capabilities because only a small subset of the simulator's features and data models are translated into the gateway. Other problem is, since there is not a universal HLA data model, you will probably have to modify the simulator gateway component in order to federate the new simulator. That is, there is also no universal gateway. Now, we will federate the vehicle virtual simulator. Here we have another problem. The simulator is not HLA compliant. It is compliant with this standard. This is an older standard that is still in use in many distributed simulators, mainly in the virtual simulation community. Therefore, we must develop another gateway to translate between this and HLA standards. At last, we will federate the C4A system. C2 system. This C2 system could be based on the DDS standard. Therefore, we will need another gateway now for bridging HLA and DDS together. Thus, using some gateways, we have developed our federation to support the training requirements we had. But what happens if now new requirements are requested by our consumers? We live in a context of rapid change, evolving requirements, and a strong request for reusability when developing system in new applications. The new requirements are very challenging. We want to use this federation not only for training but also for experimenting new systems. For example, we want to test a new version of a Hellfire missile in a virtual environment before we even build a prototype. Therefore, we want to integrate a virtual prototype of the new missile in our federation. How can we do it? Technically, the request seems easy because it is only affecting only one module of the Apache and UAV simulators, the Hellfire simulation model. But the gateway-based solution for interoperability makes it very difficult to implement. Because the Apache and UAV simulators are not open, it would be very difficult to unplug the Hellfire simulator model and replace it with the virtual prototype of the new Hellfire. HLA gateway of each simulator is only designed to deal with a small subset of data and capabilities, mainly related to interoperability in a system level. Therefore, the reusability of this federation will be very limited, and a lot of effort will be required to update it to new requirements. Now, with this example, we have shown you that simulators of interoperability is based nowadays in gateways solutions that are hard to develop, maintain, and update. These gateways designs are point solutions, not reusable and scalable, demanding a lot of resource, time, man hours, money, with a low return of investment. Gateway solutions are requested because there are a lot of different architectures, data models, and protocols. You will need a convergence of simulation architectures, and between these and the architectures in use in real critical systems in order to minimize the use of gateways. Development of a simulator with a modular but not open architecture makes very difficult its adapting and scalability to new user and technical requirements. To support the new context of evolving requirements and rapid change, we need a real plug-and-play architecture for the simulator. In the remaining slides, we will show you how the OMG DDS standard can be used to meet the challenges, converging distributed architectures for simulator and opening the architectures of a simulator. Now, we will review the different distributed architectures for simulator, its restrictions and the challenges they should meet in near future. In nowadays, simulation world is dominated by two main standards, DIS and HLA. There are also some other standards in use like TINA and CTIA. These four standards together cover more than the 90% of the market. Of these, this is the most ancient, having more than 20 years. But it is still the main architectures in a lot of simulators. As is well known, HLS was born as an evolution of this with the idea of substituting it, but it still hasn't been able to do it. All these standards have a lot of characteristics in common, but also a lot of differences. The interoperation between them is not an easy task. Nowadays, this is mainly done using gateways that translate one of the architectural words to another. Operation between different architectures can be reached, but are not practical in real joint exercises. These days, all the possible evolutions speculate on evolving HLA to something new near HLA-enhanced architecture. Let's have some historical perspective. In the beginning, it was SimNet, Simulation Network, in mid-80s. SimNet development was the first truly distributed simulation standard. Then, early in the 90s, became DIS. distributed interactive simulation as a standard based on SimNet. This was a NATO standard up to 2010, which shows its success. Today, it's still one of the most used standards, mainly in virtual simulation, because of HLA is not delivering the promised performances. Then, in the 90s, HLA high-level architecture was developed as a substitute of this and other standards like ILSP used in constructive simulation. HLA was designed as the first ever universal standard for LVC simulation, providing services for any type of simulator, live, virtual, or constructive. Nowadays, it's the main standard in simulation and is still evolving. You have had a new release of the standard called HLA Evolved, delivered in 2010. Not in the mainstream, but also important are TINA, Test and Training Enabling Architecture, and CTIA, Common Training Enabling Architecture. TINA since 2003 and CTIA since 2001. These two standards are US military standards designed to solve some of HLA issues, especially in the quality of the data distribution and in the management of the network. TINA and CTIA have improved some HLA capabilities, but are not the main industrial standards because they are not international standards and are mainly based in the use of GOTS, Governance of the Self, provided by US Department of Defense. Now, it seems that HLA is a standard that is going to evolve and win the day. But what is the future of simulation standards? Nobody knows, of course, but we can have some important clues. As suggested in 2010 LBCK study, the future standard will possibly be an evolution of HLA with some important improvements. First, this standard will have all the services of the current architectures joined and normalized. Also, it will allow full interoperability and full control of the quality of the data sending in time and space, what is called quality of service. Any new elements in simulation will be able to join any moment with a plug-and-play capability. There will be also full information assurance capabilities in this standard. Information assurance are all the security requirements for information like confidentiality, integrity, authentication, etc. These security requirements are now very, very important. Let's see some new trends in simulation. What is needed for the future? As stated in NTSA market survey and LVK study that we mentioned before, what the market demand is an evolution of HLA or an HLA-like in order to accommodate new challenges. Some of the conclusions of the reports are that current architectures have some difficult issues to solve. Different architectures and protocols cannot communicate directly. They need some translation resource. It is impossible for the middleware application to interoperate at runtimes unless appropriate bridges or gateways are put in place. There is no real plug-and-play capability. No element can join the simulation after it started. Also, the data cannot be stored and released in a historical way. Current architectures show a disparity in the services they provide. A common framework is needed. Federation object models must be reconciled across the different federations. There are different object models between architectures, or even no object model in some of them. This makes interoperation between them almost impossible, since they don't speak the same language. Also, it's very difficult to integrate legacy systems. These systems are still inactive and have to interoperate with the new developments. One question arises. Is HLA capable enough for all these challenges? Maybe if HLA is not capable, maybe some of the other architectures can do it. Let's now have a look to different architectures and their limitations and difference as stated in the LV-CAR study. How can they cooperate or evolve towards the new requirements? For this comparative, we will consider only these HLA, TINA, and CTIA. In the original study, a lot of characteristics are compared, but we will center in the characteristics oriented to joint operation in different simulators, that is, interoperability. All architectures can create a distributed simulation and allow any nodes to join. None of them allow new nodes to join after the simulation has begun. In this issue, this has some limitations. In support of publish and subscribe information, all the architectures can do it dynamically but this. In the capability to control the way the data are distributed, what is called in the study transport type, all of them support best effort and reliable. That is, you guarantee that all the data reach always destination, or you leave it to the circumstances of the net. Except again this, we have to notice that having this control is not having a real quality of service, since you still cannot control fully data distribution in space and time. All of them can communicate or interoperate with HLA through gateways. Finally, the support of multiple message types is more or less present in all of them. In summary, neither HLA as is now, nor the rest of main standards can fulfill the necessities that are required. So, what are these new requirements? All the studies considered that the list of new requirements for simulation are seamless interoperability. Different architectures and protocols must communicate directly without any significant overhead. Current gateways must unify or even disappear in the future standard. Improved quality of service, that is, full control of the data in time and space, including how these data are delivered. Fault tolerance. The future standard will allow to continue to operate when some part of the system fails. This asks for a diffusion-like architecture without any key or central node, having the data distributed all over the net and not specifically in one node. Information assurance. Security service, for example, identification, etc., that are demanded especially when the net of simulators come together with other networks that can be far away. Security is one of the hottest points to consider in a future standard. Interface with the global information grid. Everything has to communicate with this new grid. Load balancing. Balancing the workload among multiple nodes is necessary to avoid the net become unbalanced, which can make the net fail as a whole. The limit in the nets of simulator has to be to use all the resources available in all machines, not the limit imposed by the less powered machine or net. Now we have stated the problem and we are going to propose a solution, mixing together HLA and DDS. Let's start by analyzing the pros and cons of HLA as is now, including HLA Evolve. The pros, they are the HLA strong points. Since HLA is a simulation standard, HLA cares about simulation services that have proven to be very useful, also cares about data and real-life models that include inheritance. Data have to be realistic. HLA is soundly established in the industry and has many vendors. In the cons, since HLA is a simulation standard, it doesn't care much about the quality of service, the performance, for example. It's impossible to use it in real-time simulation. The scalability and the late connection, that is plug-and-play capabilities of new nodes after the simulation has started. HLA Evolved has two quality of services and performance has been improved, but in both cases there is much room for improvement. Also, there is no wire protocol to interoperate, which is a key point. Here DDS can fill the gap. DDS has been designed for real-time data distribution. All its orientation is towards transporting data in a predictable way. To do that, it has a complete suite of quality of services that allow full control of data distribution or even of local resource usage. DDS is a long-term established standard that includes an interoperability layer called the DSI that all the vendors of DDS comply. The protocol has been designed for real-time performance, so performance, low latencies, and low overheads are guaranteed. Being a publisher-subscriber system, it offers great scalability over nets and nets of nets, systems of systems as they are known. It also has fast discovery of all the possible participants and plug-and-play capabilities. Even if a node enters the simulation after it has started, indeed, a new node can join any moment without any difference. DDS offers a full fault tolerance. Data are in all nodes and there are no central hubs, and is now including information assurance as part of the standard. So yes, DDS can fulfill all the requirements and fill the gap. Since we understand that some of you are not familiar with DDS, now we will make a pause to talk a little about DDS in some detail. What is DDS? DDS stands for Data Distribution Service. Established in the late 90s, it's a public subscriber protocol that includes qualities of service that allow full control of data distribution over any net of system. Even in high noise, low bandwidth conditions it can be used. The base is having a global data space that all the nodes know and share. Thus, this data cloud is not placed in any server or central hub. The participants declare the data they want to send to the net. This is called to publish. And the data they want to receive from the net. And this is to subscribe. That way, publishing and subscribing are not coupled. The datanet is a free port where everyone can join or leave in any moment. This only leaves as a problem to solve the how to deal with the net and its possible problems. This part is solved with quality of services. Quality of services allow to control how the data are distributed in the space, the net, and in time, not before, not after, caducity of data, etc. Also, these quality of services are local properties of each element then publish and subscribe, what is called in DDS an instance. In summary, data are decoupled in time and space. They are not fault points. In this schema, scalability surges naturally since for sending data to and fro, nothing has to be known about the participants. All data interchange is in DDS an offer versus demand problem. More formally now, DDS is part of a group of standards from the OMG, Object Management Group. The first official version is from 2003, and current version is 1.2 from 2007. It has now 8 years of history. DDS is really a two-layer protocol, DCPS and DLRL. First one, DCPS, is the publish subscribe layer. DLRL is a standard for creating information. The information is organized in units called topics in an object-oriented application interface. A king of it is DDSI, now in version 2.1. DDSI, also called RTPS, is a standard for interoperability. In 2011, all the DDS vendors comply with the DDSI protocol. The standard has also a new extension for information assurance, now in beta state, and is evolving towards web and not so good nets, noisy net, low bandwidth, etc. What features of DDS are interesting for simulation? DDS was not specifically thought as a simulation protocol, but has a lot of very interesting features that can be used for simulation without changing or forcing the protocol. First, it has a wide protocol. That is a protocol for communication no matter the DDS vendor we are using, established and used by all vendors. Second, it has 22 quality of services that allow full control of data. These quality of services cover all the possible scenarios in nets, good nets, noisy nets, interruptions in communication, etc., and all possible scenarios in time restrictions. Also, they allow to control local resource usage. Third, DDS has flexibility and scalability. Any node can join anytime in any kind of net. These late incorporations are not a problem. The new nodes can even resave all data stored in other nodes, what is called historical data. Fourth, DDS latencies, that is the time of retention of data by the system, are very low. They are also predictable, and so they can be dismissed. Fifth, there are no weak points, no points of failure, no central hub. The net cannot fail as a whole. Finally, we have to note that the standard is evolving to cover no-so-good nets and information assurance requisites. Then, as a summary, we can use DDS for simulation. In fact, we NATs have been using it for the past 7 years for simulation with great success. Now we are going to compare DDS and HLA in terms of performance, output, and latency. As you can see, in all terms, DDS exceeds HLA. These results are pretty obvious since DDS is a communication-oriented protocol and HLA is a simulation-oriented standard. HLA architecture was not oriented to performance, but to real modeling. On the other hand, DDS was thought from the beginning as a layer over transport level that could be used for real-time restrictions, which in turn asks for low latencies, etc. Then, if you want to simulate, use HLA. If you want to communicate, use DDS. This is our bet. Now we have seen HLA and DDS. What we are going to see now is how this mixture can work in a real product. As a matter of resume, the challenges we address are reusability to a component level. Data model has to represent real simulation model. This includes having inheritance in the data model. Full control over the data distribution. This can be reached using quality of services. Full interoperability. Support for large-scale distributed simulation. Using the simulators together in joint exercises and in systems of systems, using them in high-quality nets and also in disadvantaged nets with low bandwidths, and of course simulation assurance requirements. The communication between simulators has to be protected from outside world, priority channels has to be established, etc. Information assurance is now a pressing matter. Mixing together DDS and HLA, we can reach an architecture like this. On one side, we can have a simulator world that we can consider a black box. This world can be a DDS simulation network. With our technology, we can make a bridge to HLA world, so we can map the data between HLA and DDS. On the other side, we can have another DDS simulator world, also bridge to HLA. All these simulators can work together at the same frequency, all sharing the same data model. From the HLA side, these simulators are federated like any other. From DDS side, HLA is another node that publish and subscribe data. Each DDS black box is a simulator by itself with all the complexity you can imagine. What only matters is sharing the same data with HLA through gateways using NATS technology. NATS provide the interoperability here in two senses. First, interoperability between HLA and DDS. This is reached using a gateway and our technology that uses the same interfaces for HLA and DDS. Second, interoperability in DDS using DDSI protocol. NATS solve the data model issue by using a HLA-like data model which includes the use of objects and interactions and at the same time is compatible with DDS data structures. This data model takes advantage of the best features of both worlds. Being an HLA-style data model, it can never be a real phone model. That way, you can use HLA data in DDS communication. So this is our proposal for solving the new simulation requirements. For reusability of data, we use an HLA data structure that at the same time can be used in DDS by converting it to the IDL format, which is the format of DDS. This process has only to be done once. After obtaining the data model, we can use it in any new element. The data can be used in any node the same way, no matter if it's an HLA node or a DDS node. The interface is just the same. For controlling the data, we offer the 22 quality of services of DDS. This allows us to control data in space and time. This quality of services can be automatically turned to optimize the data flow. Each instance, in DDS an instance is the atomic element for publishing and subscribing, can have its own quality of service. For interoperability, we can make it in two ways, as it was mentioned before. We can interoperate in the same way HLA and DDS, and we can interoperate into DDS. Finally, for information assurance, DDS offers in its standard information assurance section currently in beta state. The product that can do all this is SimWare. SimWare is the NATS solution for interoperation between HLA and DDS. It seamlessly integrates in the same interface the access to HLA and DDS. The user has only to decide, and this is critical, what data model is needed for the joint simulation. This HLA-like data model is then converted to a DDS-style data interface and made into a library. This library in turn can be used in any simulator for using the shared data model. With SimWare, you can build DDS-only simulators, HLA-DDS joint simulators, or pure HLA simulators, and all of this with the same application interface and the same functionality. With it, you can combine HLA federate with data transmission using quality of services and use all the power of DDS communication capabilities. For HLA compilance, SimWare can use our own HLA middleware, SimWare RTI, or the most common codes available in the market, MacPitch. For DDS compliance, SimWare uses DDSI wire protocol, enabling multi-vendors DDS interoperability on the wire. SimWare is a mature product and now is in version 4. Core technologies in SimWare. For application of DDS to a real-time distributed application, it has full management of simulation data distribution using quality of services. Also, allows scalable and reliable distribution over heterogeneous networks with all kinds of bandwidth, level of service, etc. It also permits easy integration of mission-critical systems for embedded training and analysis. Cohabitation of HLA and DDS in a unique open simulation architecture. Use DDS data management and distribution with HLA metadata and rules. The best data modeling with the best communication possible. Enable the development of a simulator like a federation of simulation assets. Allows an easy integration of simulation assets with critical systems. Distributed computing of simulation models. Highly modular simulation components. Ensure real-time performance with very high fidelity models. The simulator as an asset in net-centric environments. With SimWare, you can change the perspective. You don't have to worry if your simulator is an HLA, federate, or a DDS element. The simulator becomes an asset in a net-centric environment. The only thing to worry about is the joint data model. Take heed that simulators are not data coupled. DDS guarantees that publishers and subscribers are not dependent on the data model. Publishers and subscribers use the data model, and the data model is shared between them and all the elements of the simulation. Each participant declares its intentions of publishing and sends data in any moment. Also, each participant declares its intention of subscribing some data, and this data can come in any moment. With this schema, the simulator is now one asset that can be plugged or unplugged in any moment, and reused or changed. The weight is in the simulation as a whole, not in the pieces of it. SimWare as a product. NATS products are based on initial standard. SimWare uses DDS version 1.2 and DDSI version 2.1. In HLI, we follow the EEE 1516. In HLA, we are compliant with pitch, DMSO, and MAC. In this, with all vendors using DDS wire protocol, which are all vendors, in fact. SimWare is a distributed simulation framework, including libraries and tools for middleware-based distribution of simulation data, deployment of a simulator like a federation of simulating assets, interoperability of simulation assets with DDS critical systems, development of simulation models with a model-driven approach. But who is who in SimWare? SimWare is a family of products. SimWare RTI. SimWare RTI is the first HLA runtime infrastructure designed for real-time performance in large federations. That is, offers all the functionality of an HLA with the performance, power, and reliability of DDS. SimDeveloper. SimDeveloper provides a visual modeling and simulation development environment that is based on MATLAB Simulink. This tool focuses development in the mathematical and engineering modeling, not in the coding. eHost. eHost provides a development and runtime real-time framework for the development of high-fidelity simulation assets. eHost is based on an advanced real-time simulation manager which controls a high-resolution clock and the machine state of the global simulation system. This manager coordinates multiple simulation engines running in a fully distributed environment where each simulation module node can be hosted in different cores or hosts. HLA DDS gateways. The gateways are made in SimWare with the tool called Modeler. This tool allows creating and modifying flexible gateways between HLA and DDS data models. These gateways can even incorporate conversion functions between HLA and DDS data. SimWare Sim. SimWare Sim is our real-time simulation middleware based on the publish-subscribe paradigm and compliant with both HLA and DDS standard. SimWare Sim offers a unified user interface and API for distributed simulation developers. SimWare is available in 3 editions. Value editions provides IP and tools for the development of simulations with a distributed architectures. Professional editions, which are the tool Sim Developer. Enterprise editions add the SimWare RTI that gives a real-time HLI middleware that take advantage of DDS features of real-time distributed simulation and also of HLA. SimWare RTI HLA middleware is also available alone as a separate product. Both of them can come in Windows or Linux in 32 and 64 bits. Now finally, let's see some real use cases of our technology. Build a federation of simulation assets for the Spanish Ministry of Defense. In collaboration with the simulation laboratory of the Ministry of Defense, that is called ITM, this project allowed to develop an infrastructure modeling simulator. The project allowed to develop a development environment for simulation models, a simulation model test bench, also simulation models that could be used in the development environment. All of this based on existing technology of SimWare, evolving the modeling structure based on MATLAB Simulink. CATIA demonstrator for Navantia Faba. In this case, the project main objective was to evaluate the ability of SimWare technology to meet the requirements applicable to simulate the sensors with which the combat system of the CATIA program will interact. These sensors have requisites of functionality and performance in real time. The elements of simulation, 3D radar, 2D radar, that communicate with the combat system will obtain information about radar contacts and their on-SIP information from a common contact generator. The project simulates over 200 contacts in real-time simulation, 10 Earth, with TTS and SimWare. Infrared simulator for CLAEX. CLAEX is a Spanish Ministry of Defense center. The project main objective was the delivery of an infrared simulator to CLAEX. The main use of the simulator was to improve programs for dispersing flares for various weapon systems. The project included the use of MATLAB modules with SimWare Developer to model all the flares' behavior. All the simulation was made using SimWare over Windows. And now a work in progress. In this schema we can see the architecture or reference of the Spanish Army. In this architecture we have tactical elements and strategical elements, both joined with DDS as a backbone. Here, NATS is proposing to complete this schema with addition of real, constructive and virtual simulators. In this case, the protocol will be HLA, and there will be a gateway between DDS and HLA. All the interoperability using HLA and DDS could be done using SimWare technology. So this is the end. Can the future be like this? HLA and DDS operating in the same joint infrastructure. The exercise not caring about the infrastructure, all in a common net. The nodes not caring about the quality of the net or about language. All the exercise centered in the joint simulation. All the infrastructure transparent to the simulators and all centered in data sharing. Underneath, HLA and DDS collaborating. With SimWare, this future is possible.